Hello, everyone. I am Kim-Adeline Miguel. I am a software engineer on the Python extension for VS Code, and today I will talk about Overwatch and Python. So this is Decoding Bias and Narrative in Competitive Video Game Broadcast with Video Analysis. So in this talk, I will discuss some assumptions and hypotheses around what is shown to viewers of video game tournaments, and I will use the first-person shooter Overwatch as an example. So first, a little bit of legalese that none of this belongs to me. And then, so the outline of this talk, how it is going to be structured. So first, I will start with the motivations behind this talk, like how can somebody come up with this idea in the first place? And then I will describe how I built the video analysis system, what I used, the choices I made besides using Python, what went well, and what could have gone better. And then I will do some number crunching and compare the results of that number crunching to the hypothesis I made in the first place. And I'll just end with the summary of my takeaways from building this project. So first, why this talk? Why are we here today? So if there was one thing to remember, it would be because I could. But it's not just that. So as I said, I work on the Python extension for VS Code, but I am a front-end developer by trade. I am more comfortable using JavaScript or TypeScript. So I decided to come up with a side project to learn how to use Python better. And I thought it would be about something I like. So I like playing Overwatch, and I like watching people play Overwatch, especially pro players, because they know what they're doing. So I figured that would be something around that. And then I won't go too deep there, but it is good to challenge what the media shows you every so often, like the content you ingest. So this was a little bit of thinking outside the screen, thinking outside the box. And I decided to challenge those assumptions using hypothesis-driven validation. So state some hypothesis, gather data, and use the data to validate or invalidate those initial hypotheses. But before we get started, I will give a quick rundown on eSports and Overwatch. So first, eSports has multiple spellings, as you can see here. So according to Wikipedia, it is a form of sport competition using video games. So if you take the top 5 most popular video games in 2019 and you add up the numbers of hours watched, you end up with 1.1 billion of hours watched. That's a lot of time spent staring at somebody else playing computer. So those hours watched can be on online platforms like Twitch or YouTube Gaming, but also with traditional TV channels like ESPN, ABC in North America, or OGN in South Korea. And sometimes the channels, whether online or traditional, can also work out exclusive broadcasting deals. Then how does that tie in with traditional sports? There are a lot of partnerships. Like, it is not uncommon to see owners of traditional sports team invest or have stakes in esports organizations. Then there's also endorsement deals, just like with regular athletes, like ads or sponsored content, or just simply moving some items around so that the brand faces the screen, faces the camera, right? And then there are also league and franchise systems in esports, where if you want to compete in the topmost league, you have to buy a spot that is worth a couple $1 million. So it's virtual sports, but there's real money going around in this industry here. So esports, that's great. And since this talk will focus on Overwatch esports, let's start with what is Overwatch. So Overwatch, according to its website, it is a colorful team-based shooter game starring a diverse cast of powerful heroes, travel the world, build a team, and contest objectives in exhilarating 6v6 combat. You can play it on PC, Nintendo Switch, PlayStation 4, Xbox One, but here we are going to focus on the PC game. So that was the description of it. But so what happens when you enter a game? So it's a first-person shooter that is set in the near future on a fictionalized Earth, which means that most of the maps in the area you're going to visit are locations, like real locations, although some of the traits and structures, also some of the decorations in there are going to be heavily fictionalized and sometimes exaggerated. So it's 2 teams of 6 that compete for objectives on different maps. Usually it's a variation of attackers and defenders, although there's a map that is King of the Hill where you have to capture a point and then keep the point for a certain amount of time. Because of that, there are multiple rounds in each map where people swap roles, like attack or defend. Now, what does it mean for you? In your team, there are 3 roles: tank, damage, and support. And you have 32 characters named heroes you can pick from. It's just you need to have 2 heroes of each role per team. So 2 tank, 2 damage, and 2 support heroes. Since Overwatch is catering to a varied audience, there are many different types of heroes with different abilities. Some of these heroes can be a little bit stereotypical. So, for example, there's the big guy with armor to protect you and absorb damage. If you want to deal damage, you can be a badass cyborg ninja. Or you can also be a literal angel to save and heal your teammates. They also have heroes that are less cliche. So you can have a strong lady with pink hair to absorb damage, a winter lady with a tiny robot to deal damage, or you can also be a robot that lives off the grid to heal and support your teammates. So that was Overwatch. And now Overwatch and eSports enters the Overwatch League. So the Overwatch League, also abbreviated OWL, is a city-based franchise league. So the team names are city-based, like Boston Uprising or Vancouver Titans. The games are streamed on YouTube Gaming during the weekend, so you can watch them online. And each game between 2 teams is made of multiple maps. So the win conditions right now are the first team that gets to 3 map wins. And remember, each map has multiple rounds. Each team has a roster of up to 12 players, but since only 6 of them can play at a time, the teams can swap players between maps, but not between rounds. So you have the games every weekend, so you can like have a watch party with your friends or not, like sit with them and watch the games, just like with traditional sports, and cheer every time there's some action happening on screen. However, in traditional sports, the camera follows the ball because that's where the action happens usually. Here, there's no ball. There's 12 people running around trying to secure an area, and sometimes the area can be moving as well. So what is the action here? Who decides what is it? This is the question behind this whole project. So in order to try to answer this question, I have come up with a set of assumptions that we will then try to answer. So first, even though it's a team-based game, people want to see the stars because they want to identify with them, see the people who make the big plays. And so people would rather watch the damage heroes. You want to be the badass cyborg ninja. So that was for the role bias. Then for team assumptions, do people want to cheer for the underdog team, or do they want to cheer for the team with the better win percentage? Also, would people rather watch the team that is winning the game, or is it more balanced on each side? Are those hypotheses, are they what the viewers want, or what producers think the viewers want? Or what the producers want the viewers to want. Like there's a lot of layers to unfold here. Anyway, I'll just leave you with that, and let's just start building this system in Python, of course. So first, so that's a screenshot of a game broadcast. You can see here that it's a first-person point of view. There is a lot of data here that is readable and visible on the screen, but we are going to focus on what's in the bottom corner here with the name of the player who plays the hero. And we are going to use this data to try to determine whether our hypotheses are valid or not. So the process, how we're going to do it. So given a broadcast, the video of a game broadcast, we're going to extract frames from this video. Then we're going to crop those frames to only keep the relevant area with the player name. We're then going to send those images to the optical character recognition system that is going to send us back the player name that was contained in this image. Then we're going to store that data somewhere, probably in some kind of database, and compute stats from them. If you're more of an architectural diagram person, here's the architectural diagram slide that just states back what was in those bullet points. So you have the video, you split it into frames, then you crop the frames to only keep the relevant area, then you send those images to the optical character recognition system that then returns you a list of names that you store somewhere, and then you do some number magic to get charts and data. So that was the theory. So in practice, first, this was for me to learn Python. So when picking packages, I wanted something that had minimal setup so that I didn't have to fiddle around with environment variables or other obscure setup. So the lesser setup, the better. Then I wanted something with reliable documentation so that I wouldn't have to search the internet for every single problem I was going to have. And I also wanted something that was relatively popular so that if I had to search the internet for answers, I wouldn't be the only one having that problem. So then the process, it starts with splicing the video and extracting the frames. For that, I use the FFmpeg, which is a command line-based utility tool for processing video and audio files. It's a very advanced tool, but also very accessible to beginners, and it's also well used. Even though it's command line based, it also has a Python bindings so that you can use it directly in your Python code without having to spawn a process. So pip install ffmpeg python and you're good to go. Then once you've spliced the video into frames, then it's time to crop the area. So why I crop the area in the first place? First, I didn't want to send the entire screen to the optical character recognition system. Like you saw, there was a lot of data there, and so I wanted to not only minimize the noise of all what could be read, but also just minimize the amount of data being transferred. So for area cropping, I use Pillow, which is the fork from the Python imaging library. It is a reference in terms of image processing. So far, FFmpeg and Pillow are just nothing to say here, nothing special. Very used, lots of documentation, no problem. Then we move on to the player name parsing, the optical character recognition system. So because I crop a static area, it's always the same rectangle that is being cut. However, one of the game details is that the bottom bar bounces in game with player movement. So if the player jumps or if the player crouches, then it's going to bounce up and down. So that's why you can see in those samples there that it's not always in the same spot. And then there's like team-specific colors being applied to the names so that viewers can identify with the team. So there's many a few different kinds of images that had to be parsed. So first, I wanted to try to do it locally using the Tesseract OCR package. However, it didn't really work so well. It couldn't really read that font, and also the colors, it didn't like the different colors either. So on my second attempt, I used the Azure Computer Vision Services. First, they have a web page where you can try it out, and it worked. So I was like, yes, let's do that. So then to use it with Python, so you can either make REST API calls directly, or you can use their package. So you do pip install Azure, I don't remember the rest, and you can just use the classes and methods they provide you to make those calls directly. For those of you who are worried, there is a free tier. You don't have to hand out all of your information to them, nor your credit card number. The free tier is 20 calls per minute and a maximum of 5,000 calls a month. So make sure to not go over those limits, or you're going to be in for a bad time, aka your calls are going to be denied. I definitely did not get there. So this Azure Computer Vision Service Library, so they have two types of calls for optical character recognition. So they have asynchronous calls, which is what they call the read API, that can read printed and handwritten text. And they have synchronous calls, which is the OCR system, which only supports printed text, like, for example, a PDF or something. I first tried the synchronous calls, but it didn't work. It could not process those images either. And it turns out that on their test website that has great results, they use the asynchronous API. So I had to do that. So basically, for each image, I had to open it, serialize the data, send it to the service, and then poll the resulting URL for a response. And when it is marked, and when the response is marked as available, then I would have to retrieve the result. When testing this, I also saw that I needed videos of at least 720p. Otherwise, the quality of the text was not enough for it to be able to read anything. I could have sent full HD videos as well, but then again, a lot of data sent for not much reward. Remember when I said that the status bar was bouncing? Yeah, it also meant that sometimes it would cut things where they shouldn't have been cut. So after sending all my frames to Azure, I still had to do some post-processing sanitizing, because sometimes the system did not understand the names as I wanted, or I just sent it truncated versions of the names, and I had to fix it manually. This will go in the what could have gone better slide. Then, now that we've parsed player names, we have to store them somewhere. So I know that database choices can be very opinionated. So here I am just going to refer to my package picking guidelines. I want something with as minimal setup as possible, with good documentation. And if it was popular, then it would be good. But first and foremost, minimal setup and documentation. So that's where I found TinyDB, which is a lightweight document-oriented database optimized for your happiness. That's what they say. So I used it because it has no external dependencies. I could just do pip install, and I think it was pip install TinyDB, and just get going. Then it's document-oriented, so it stores documents and not rows like in a relational database, and they're stored as dictionaries. What this meant is I only had to work with JSON files, which was great. So using TinyDB, so the way I stored the data in there. So first, I had a static table with teams information. So this would not move. This was like my reference point for all the work. Then when I parsed each map of each game, I would have one database per game. And in this database, I would have one table per map. And for each table, I would have entries for each frame. You can see on the side here, that's an example of a table, like of a map table. So this would be map 3, Volskaya, for a game with the Vancouver Titans, and I don't remember where Leave is, but you see the map table, and then as many entries as there are frames with the player name and the frame number, because the frames were not parsed in order. So now we have stored the data. That's great. Time to make something out of it. So first I was plotting the data using Plotly. So Plotly is based in Montreal, so support your local businesses since I'm in Canada. And it's a browser-based graphing library. So basically, I would create a plot and do plot, and it would just open in my browser with the chart, which is what browser-based graphing library means, right? Plotly.py, which is their Python version, is a wrapper around their JavaScript library. So if you were to be a JavaScript person, you might want to use the JavaScript one directly. So that's when I wanted to make single plots. But then I was like, what if I could put 2 plots in one page, right? And add some text to it, maybe. So that's where Dash comes in. Dash is also made by the people who make Plotly, and it combines Plotly.js, React components, and Flask web servers. So you can build like Python web apps using React components to add text and annotate the plots that you make. You can see the screenshot here is when I started my code. That starts the dashboard. It would basically start a Flask application. So still something I know how to use. So here's an example of the charts that I made. So here, for example, the game is Philadelphia Fusion versus Atlanta Reign on map 2. You see I have some team stats that could have been like rounded. But Philadelphia had 55.17% screen time compared to Atlanta's 44.82%. And then you have the on-screen time for each role, damage, tank, and support. And then on the chart, you could see the role distribution, like damage, tank, and support. And on the chart on the right side, you have the team distribution, like Philadelphia or Atlanta. For somebody that applied a style to all her PowerPoint slides, I could probably have made better charts, but I was just glad it worked. Please don't judge me too hard. But at least there's charts, right? So what could have gone better? So one of the first areas of improvement would have been some dynamic player area cropping, or at least some dynamic parsing of the player area since it was bouncing. You can also see the character recognition system limits because the cropping was not reliable, then its output was not always reliable either. So I could, going fancy, there could have been like a machine learning system that would have been able to know which area to crop. Or I could also have cropped like the entire bottom left quadrant of the screen and just done some extra parsing to know what text is the player name compared to the health bar or their player number. Then the packages that I picked, because I wanted minimal setup and documentation, I could have made some better choices. There were other alternatives, and I was not worried about performance at all. So if it was a high scale operation, then I would probably have to revisit the packages I used to build the system. But because it wasn't, then it just went with what I found. And also, last but not least, really, those charts could have looked a little bit better, probably by leveraging other packages or reading the documentation a little bit further of the plotting library to find a chart that would have been more appropriate for what I was trying to plot. Anyway, so that was the system, and now time for the results, the findings from parsing all those games in this system. So as a data set, I used the Overwatch League games from week 10, so from the weekend of April 11th and 12th. So there were 10 games. Spoiler alert, I also put the scores of the games in this slide. So if you haven't watched them, please close your eyes. It's a bit late, but please close your eyes. So here are the 10 games that I used in my data set. And also I wrote down the standings before the game started. So like the score of each team that participated in those games, so their wins and their losses. Some teams have played 2 games during this weekend, so some of the standings might have changed halfway through, but I did not take that in consideration for this project. So now with the standings, I could compute the win percentage of each team. So the number of games they won over their total number of games. So given this data set, we can try to verify our assumptions. For those who did not remember what they were and do not want to go back in time in the video to see the slide, here it is. So here are our assumptions and hypotheses. So first, people would rather watch players on damaged heroes to be able to identify with star players. And then do people want to cheer for the team with the lower overall win percentage, or do they want to cheer for the team that is going to win, like kind of bandwagon fans? And then do people want to cheer for the team that is winning the game, or would they rather see a more balanced on-screen time? It's time for the big reveal. So first, role distribution. So over those 10 games, the average on-screen percentage per role is heavily skewed towards damaged players. You can see that varies a lot. Like you have games with only 49% of on-screen time on damaged heroes, but games where 80% of the screen time was for damaged heroes. Then tanks have on average like a little bit more than a quarter of screen time, and supports are, as usual, not being featured that much. There were some maps where there was no support on screen time. This is so sad. So now that we've seen the results per role, let's see the results for each for the teams. So the average on-screen time difference between teams is at 9.71%. However, this doesn't really cover all the data, because depending on the game, there could be almost 30% on-screen time difference between the two teams, or games that were more balanced with only a 0.3% difference. So there's that. Then 8 games out of 10 were so that the winning team, so like the team that was winning the game, had overall higher on-screen percentage compared to the other one. Then there were only 7 games where the winning team had higher on-screen percentage for most of the maps. So, for example, the team with the higher on-screen percentage might have a higher percentage when you combine all the maps, but not on the map-by-map basis. Then there were only half of the games where the team with the better win percentage, so like the better win-loss score, had higher overall on-screen time. What do all those numbers mean? Well, does everybody want to play damaged heroes? Probably, since damaged heroes get the most screen time by a large margin. Then, how much do people like underdog stories? Given there was a 50-50 split, I will let you decide on how to interpret it. Then our third hypothesis, do people want to cheer for the team winning the game? Well, even if they did not want to, that's what the producers are showing in 8 games out of 10. Anyway, there were other elements we could have used in our data analysis. So first, other elements on the screen that we have, like when parsing those videos. So there were other readable elements, so like the team names, the different like statuses and percentages at the top, but also like the map number, the win progress that we could have read, like also parsed in the optical character recognition system. But there were also other camera shots that we could have used. Like in this project, I only used like first-person point of views. But you can see here in this screenshot, it's not a first-person point of view, but it still features a lot of members of the red team, Atlanta. So this could have counted as this could have counted as Atlanta's screen time as well. But because it was a little bit more subtle, I did not parse this kind of data. So now there's also other kind of data that was not like readily readable on the screen. For example, the per map outcomes, like I did not consider which team had won or lost each map, only considered the final result of each game. Then also completely discarded the audio track, like the casters sometimes emphasize one player over the other, and this could also count as screen time. And last but not least, the sample size. Like there were only 10 games. Like I only worked with 10 games, and you could see in the standings that not all teams had played the same amount of games. So this also somewhat skewed the results. We're almost there. Too long didn't read, a summary for everybody. I will start with this tweet screenshot that is very accurate on why I built this project. So I started with some assumptions, and then I followed a scientific method and came up with some conclusions that I outlined in this talk. But besides that, besides that, in this talk, we built a video analysis system in Python that takes a video as input and outputs human readable numbers that you can use to do some magic. It wasn't so bad. Well, I don't think it was that bad. Both the video analysis and the hypothesis-driven development, like we had some hypotheses and we managed to confirm or invalidate them. It worked out. But this also means that data can tell you anything and nothing at once. Like you can interpret those results however you want. So we only scratched the surface of what can be extracted from this footage. Like as I mentioned, there are other kinds of data that you can extract from those videos and that you can parse. Now, whether the parsing I did was Pythonic or not could be discussed in a separate talk named Undo That Semicolon like right now and other best Python practices. But at least this was a good starting point to use Python and perform video analysis. So I hope that this has inspired you to do something fun or something video game related. If you want to see Python code written by a JavaScript TypeScript developer, here's the link to the GitHub repo. You can also send me a message on Twitter if you have any questions, concerns, ideas, want to say hi. And that's it. Thank you, everyone. GG well played. And before we end, here are links, and more links.